So in the last class we finished this proof showing that pH is in p to the sharp p, and then we started randomization as a resource in Turing machines, right? So we call it probabilistic Turing machine. So BPP is the first class we define. This is essentially probabilistic Turing machine, which is polynomial time. It's basically what we can call it probabilistic polynomial time or randomized polynomial time algorithms. And this is a very fast version of PP, you can say. Okay, it's between P and PP. And then we were looking at examples of such algorithms, which are very practical algorithms. They are widely used. So first is the question of primality. Okay, given a number n in binary, is it prime? So for this, the randomized algorithm that was first given by Solovay-Strazen is pick a random a, number a, and then compute this exponentiation a raised to n minus 1 by 2 mod n. This will come out to be plus minus 1, and you compare it with the Jacobi symbol a by n, which is also plus minus 1. If the two are the same, then you output yes, n is prime, otherwise you output no. You can show that this has one-sided error. No error on prime, on n prime, but some error on composite n. And this shows that, let me call the class primes. This shows that the class primes is in BPP. You can actually make the error probability smaller than 1/3 by boosting. Boosting also we will see in this class. Because of one-sided error, you can actually show that it's in BPP. Okay, the second example will be that of polynomial identity testing. So what is this problem? So as the name suggests, you want to test for identities. Okay, whether some expression A is equal to another expression B. So we formalize it as follows: given a polynomial in n variables and some coefficients from some field big F in a compact way. What's a compact way? For example, as a circuit. Okay, so algebraic circuit expresses a polynomial in a compact way. You can add inputs coming on the wires, or you can multiply inputs coming on the wires and then give an output. Okay, it's towards the end of the course we will define what a circuit is, but just think of it from electrical engineering viewpoint. That is where the name comes from. So polynomial is given in some compact way and you want to check whether it is 0. So check whether f is the 0 polynomial. Okay, so being 0 is what is called an identity. So you want to check this identity, test this identity. Now you can show as an exercise or let me, in the previous style, let me give the algo. So the algo will be, the algorithm is just pick a random point alpha from f to the n and output yes if f alpha vanishes. Okay, so on a random point, if f vanishes, then you suspect it to be identically 0, an identity. If it doesn't vanish, then you know that it's not 0. You output no. Okay, and show that this is a good algorithm. This is a good practical algorithm that you can utilize. So again, you can show here one-sided error of 1/3 or whatever you want, actually, assuming that the field is large. So you basically, that is one thing you will need. So without loss of generality, you assume that the field is more than, I mean, let me just say field is large. Okay, so if the field is large, then with a small error probability, this algorithm will work, and it's also one-sided, because in the when f is 0, then it will always say yes. If f is not 0, then it may make an error, but the error is limited by 1/3 probability. And again, this means that PIT is in BPP. Show that. Okay, this again is by boosting the probability. And there are other examples. In fact, many other examples. So for example, finding square root. Modulo a prime. In graph theory, there are many examples. Finding a matching. So matching has a randomized algorithm, or as I once mentioned, also connectivity. So undirected connectivity in log space. Okay, that also has a randomized algorithm. So there are many such things, many such problems which have randomized algorithms, either in polynomial time or in small space. So this is going to be a very useful resource, especially for practical algorithms. Okay, you can see how these are all nothing but probabilistic Turing machines. So what is open here? There are many open questions about probabilistic Turing machines. So first is whether PTMs are needed. So whether PTMs are required. Okay, that is the question of whether P is equal to BPP. So let me say, are PTMs really needed? Are PTMs really useful in terms of efficient algorithms, or can every PTM be converted into a deterministic Turing machine? Okay, so that is the question of P equal to BPP. It is conjectured that PTMs are actually not needed, up to polynomial time. So there is theoretical evidence for yes. There exists theoretical evidence. In favor of this, okay, which you can see in a more advanced complexity course. Second question is this probabilistic certificate R weaker than the NP, the certificate that a verifier needs? Okay, so it is conjectured that BPP and NP are different. So this probabilistic certificate is much weaker than the non-deterministic certificate. In fact, later we will show, else pH collapses. Okay, so we will see later that if BPP is NP, then the polynomial hierarchy will collapse. So again, there is theoretical evidence for BPP not equal to NP. So as I have said many times before, BPP captures probabilistic algorithm with two-sided error. Okay, so the error can be on the yes instance but also on the no instance. That is, if a PTM M decides L, then it may make an error on X regardless of X in L or X not in L. Okay, for yes instance it can make an error, for no instance it can make an error, but the error has to be limited by 1/3. That gets important. Half is not enough for practical algorithms. So let us investigate this further. What happens if we consider one-sided error, like we already saw in example algorithms? So one-sided error defines classes RP and co-RP. Let's define that formally. So a problem is said to be in R time if there exists a probabilistic Turing machine running in time big O of Tn such that X is in L, so on yes strings so let me define PTM M. The probability that M accepts X or simply Mx equal to 1, this probability should be as in BPP, but if it's a no string, then this probability should be 0. Okay, so this is the part which is unlike BPP. Okay, in BPP definition, some error was allowed here also, but in the definition of R time or what we'll call RP, there should be no chance of error on no strings. On yes strings, there may be some error. Okay, so that is what R time is. Running in that many steps, big O of T of n. And yes, so then you can define RP. So the class RP is over all polynomials. Okay, and this you can read as randomized polytime. Okay, so sometimes BPP, RP, co-RP, all of these we call randomized polynomial time. And some quick observations that immediately follow from the definition. So first is, where is primes? The example that we gave, right? The example algorithm. So this famous randomized polynomial time algorithm by Strazen, Solovay-Strazen, this could make an error in the no instance, but never in the yes instance. So it's the opposite of RP, it's co-RP. So primes is in co-RP. Okay, by the earlier algorithm. So that's actually a co-RP algorithm. Okay, errors on no, no errors on yes. Oh, sorry, yeah. So yes, no errors, and no, there may be errors. So same thing for PIT. This is again by the previous algo. Now any RP algorithm is also a BPP algorithm because the error restrictions are there, right? Both sides the error is less than 1/3. So this is automatically in BPP. Okay, RP and co-RP both are in BPP. Now what is the relationship with NP? So one good thing in this definition of RP is that so let me change this a bit. So mx comma r, the random bits, and the probability is over r. Right. So now if for some random string or for some string r, m accepts x, then it must mean that, then it has to be the case that x is a yes string, right? Because for no string x, there is no such r. So actually here R is a certificate. Okay, so RP problems are actually in NP, they are certifiable, and similarly co-RP is in co-NP. Right, so this is because R is a certificate. And the PTM M is the verifier. So note that on the other hand, we don't know whether BPP is in NP, right? So that is in the definition of BPP. The R actually doesn't certify because error is on both sides. So just by finding an R such that mxr is 1, you are not really sure whether x is in L, whether x is a yes string. Okay, so this was not really clear. It didn't really mean that it's in NP. Okay, and yeah, can we use PTM where with no error? So are there PTMs with no error? Yeah, there is a way to define this and still not being completely deterministic. So we can do this by make the time complexity a random variable. Okay, so we can talk about what the time complexity is. We can talk about the expectation, and that is called zero-sided error probabilistic Turing machines. Okay, so that's ZPP complexity class. So it's this class will capture probabilistic Turing machines which make no error, but yet the time complexity is not deterministic. Okay, it's a random variable, so you can talk about its expectation. These are also called Las Vegas algorithms. So let's define this. So consider probabilistic Turing machine M and the random variable time complexity of M as a function of the input on any input x. So we say that M has an expected running time Tn if for all inputs x the expectation of over the random bits that M will use. Okay, the expectation of this time complexity is, or in fact number of steps, is T of size of x. Okay, so notice that we are not talking about any error. There will be no error, but the number of steps may be exponential, doubly exponential, whatever, but then expectation will be T. Okay, so as for the same x, as you change R, usually time complexity will be T or smaller. And based on this, we can define Z time. So L is in this complexity class if there exists a probabilistic Turing machine that correctly decides no errors made, although random bits are being used, but error is not made. L is decided correctly in expected time around T of n. Okay, so the expected time complexity is around to the order of T of n. Then you say that L is in Z time Tn. And this, as always, immediately defines your notion of efficiency, which is ZPP. In this case, it's the union over Z time n to the C, right, all polynomials. Now this is an interesting class. It has quite interesting properties. You can actually relate it with BPP, RP, co-RP. So let's do a simple yet non-trivial proposition. So ZPP is in RP intersection co-RP. Okay, so what this is saying is that ZPP is actually a better algorithm than RP and co-RP. Okay, so these problems are potentially more special than the problems in RP. And obviously, in the previous proposition, we have shown that both RP and co-RP are in BPP. So all this business is happening inside BPP. So this set of algorithms, they are called Las Vegas. Okay, so the randomized algorithms of the ZPP type, they are called Las Vegas, while randomized algorithms of BPP type, they are called Monte Carlo. Okay, so these are some old-fashioned names, but we'll just refer to ZPP, RP, co-RP, and BPP, and this is the relationship. So notice what you have to show here is that this no error or zero-sided error, this can be reduced to one-sided, but then the time gets fixed to polynomial. Okay. So the idea is that ZPP algorithm time is unlimited. You truncate at some point. Okay, and then show that the error probability will be bounded. So you get in RP. This will be an interesting property. Second interesting property is, or more interesting property is that if a problem has both RP and co-RP algorithms, then you can combine those two and get zero error. Okay, so intersection actually is equal to ZPP. That's the third property. So ZPP is actually RP intersection co-RP, and this RP is in NP, yeah, right? That you remember. So this is in NP intersection co-NP. Okay, so RP, co-RP, ZPP, they kind of overlap, and these are very special algorithms. Okay, in fact, you can also, this is between P and NP intersection co-NP. In particular, you don't expect ZPP to be solving NP hard problems. Okay, otherwise the hierarchy will collapse. Okay, so let's see the proof. Let L be in ZPP let it be decided by a probabilistic Turing machine M with expected run time T of n. Now you want to show that L is in RP. So let's do that given algorithm. So on input X, what you do is you run M of X for 3 times the expectation. Okay, so expected runtime is T of n, you run it 3 times the expectation, and if the answer has come, it must be correct, output that. If the answer hasn't come yet, output no. So if so output no, if and only if X is not accepted. In these steps. Okay, so if X remains unaccepted, the machine did not decide anything, you output no. If the machine decided and said yes or accepted, then you say yes. Or if the machine has rejected in these many steps, then obviously you say no. Okay, so do this, and let's now analyze this from from RP perspective. It actually shows that L is in RP. So if X is a no string, then definitely you will output no. Right, because you will simply not see yes in this green algorithm, so you will output no. So that's correct, no error. If X is in L, then what is the chance that the algorithm will not stop in 3 times the expectation? Okay, so that chance is smaller than 1/3. So let me name this actually M prime. So probability that M prime X this new algorithm M prime rejects X, this probability is the same as probability that M on X takes greater than 3 times T of X time, which is less than equal to 1/3 by the definition of expectation. It is also called Markov inequality. Okay, so by Markov inequality you get probability less than equal to 1/3, which means that we have shown on yes there is some error, on no there is no error, so L is in RP. Similarly, show that L complement is in RP by a similar approach, and this means that L is in RP intersection co-RP, okay, which means that ZPP is contained in RP intersection co-RP. Okay, so that proves the first property.